Hello, can you hear me?
Yeah, Dr. Wiktor.
Give me just a second because I think that my camera is not working.
Yeah,
Let's try it again. Oh, you should see me now. Can you see my presentation?
yeah. Please go ahead.
Great. So, hello, my name is Wiktor Sus. I am a PhD student at AGH in Krakow. The topic of my today's presentation is adaptive resource usage prediction in cloud computing context, related to my current research area of short-term and long-term resource usage prediction in distributed computing environments utilizing anomaly detection mechanisms. Let us begin by deciphering the meaning of the title by explaining what is resource management in cloud computing. This term describes the task of allocating the resources needed for customer services, either via the customer or the cloud provider. These resources can be low or high level, depending on the context, and they can include CPU, memory, disk, and network usage, and others similar. The high-level resources can be virtual machines count, for example, when using AWS EC2 service, or pods, when using Kubernetes cluster. For the sake of simplicity, I'll keep using pods as an example, since they can be easily understood in terms of scalability, as more pods mean more agents handling the load usually. These resources are in general used by the service, so for example, if the customer runs a website, then the pods may be handling the load distributed by a load balancer and serving it. To keep it operational, there needs to be a sufficient amount of pods available, or the user will experience a website timeout. The customer wants the users to use their service in order to keep their business running, so they'll want to make sure that the service can handle the load. This is done by reserving surplus resources to handle the sudden spikes in usage. However, this approach induces additional costs, and when there is lower load, the resources are wasted. As I mentioned, there needs to be a sufficient amount of resources. To ensure this, they can be either managed manually by the operator or automatically. Manual management, however, quickly becomes infeasible when managing large clusters, especially when they are handling multiple parts of the service and require different resources. Therefore, automated solutions are used. They are most commonly rule-based, as in when certain conditions are met, the changes are made. For example, when average CPU load percentage of all pods crosses certain threshold, new pods are added. These are reactive solutions, meaning that they change the reservations depending on the current system change state in response to it. The second type of automatic solutions are predictive, which makes such changes ahead of time. The reactive solutions are sufficient in most cases. However, they suffer from a serious flaw, the overhead time. When changing the reservations, especially when scaling up, creating new pods, they need a certain amount of time to be set up, which can take up to minutes. When facing huge spikes, this may not be fast enough, and the currently active pods may become overloaded, and the whole service may go down, since new pods will receive more traffic due to the currently active ones being overloaded. In worst case, this can lead to a cascade effect of cluster constantly scaling up and being unable to keep up with the load. To prevent this, a predictive system can be used. Predictive system makes the changes to the reservations before they happen, based on the predictions, allowing the pods to start up before the spike. This also allows the customer to reduce the safety buffer meant to handle such sudden changes, since the prediction system can prepare the safety buffer when needed, reducing it when it is not required, which therefore reduces the cost for the customers. You may now be wondering why such solutions are not widely used yet. This is because even though they are quite useful, they have a couple of downsides, and there are still some challenges with their introduction. The first, and perhaps the biggest problem, is that they can only be used in scenarios when prediction is actually possible, meaning in cases where the load is not completely random. Otherwise, the prediction makes no sense, as it is not possible to predict noise, which by definition has no patterns. Therefore, the best candidates are user-facing services whose load may vary with the time of the day of the week, or other. These could be online shops, websites, or other similar services. Next challenge is training such models. While there are many cloud datasets, they are quite often limited either by the time span of measurements, most often up to a month, the amount of machines analyzed, its age, because preferably the dataset should be relatively recent, and its quality, the labeling, noise, missing measurements, and other such factors. Finally, the live datasets may contain anomalies which affect the prediction accuracy although their impact can be reduced by introducing anomaly detection methods. There is also an additional problem with prediction models, which is a drift. A drift in machine learning is a phenomenon which occurs when, due to various external circumstances, the model becomes outdated. This can, for example, include changes in services usage due to its increased popularity. When more users become interested in the service, the baseline usage may change. This causes the model to underperform since it was not trained to deal with such scenario. This can be further highlighted by the seasonal trends, when certain aspects are affected by holidays or other real-world events, such as, for example, major sales like Black Friday, which greatly affect traffic in online shops. To handle them, a dataset with large time span is required, and as mentioned before, these are hard to obtain. This brings us to the point of my presentation. I propose a solution which utilizes multiple models in an ensemble fashion with the use of novel signature-based selection method. Ensemble prediction is already known to increase the accuracy, and this is the idea of the solution. Ensemble prediction is not new in itself, however, a signature-based approach has not been tried before, to my best knowledge. Additionally, the proposed solution utilizes heterogeneous models, meaning ones of different types, as opposed to the same type but different configurations. The models included are some of the state-of-the-art ones. In this example, the dense network, long short-term memory network, autoregressive network, and convolutional network are used. There are other good models, such as ARIMA, which however was not used in this example since it requires stationary dataset which cannot be easily ensured. The general idea is to combine diverse models with high accuracy and possibly different specializations into a single ensemble, and by using a selection function, decide which one is the best suited one at any given point in time. The selection function uses the recent data from the system and can generate signatures describing the current system's behavior. For example, whether it's chaotic or stable. Such signatures can then be used to select best prediction models from the available ones. The solution can adapt to the changes dynamically and can be further improved by including anomaly detection module. Also, new modules can be easily added due to its extensible architecture. This approach is called dynamic selection multiple classifier system, which describes an ensemble with multiple classifiers or regressors and a selection function which selects the model to use at given time. There are many variants, such as weighted one, which utilizes weight from the various prediction model incorporated to select one proper prediction, or the ones which output a single prediction. This architecture has been researched extensively, however, there is no one single best selection function known at the moment. Due to this, the proposed system utilizes a new signature-based function tailored for cloud computing, which allows the ensemble to respond to behavioral shifts in resource usage. The signature generation is a process of obtaining feature vector representing the current system's behavior. It is obtained via various calculations and include metrics such as entropy, which denotes the system's stability, or how chaotically it changes, amplitudes, speed of changes, and other. The selection function then matches the signature to the best performing model. The idea is that since the system may be undergoing periodic changes, the changes themselves could be described with such signatures, and this could allow the system to use different models since they may be better suited to certain types of changes. The solution was evaluated on a real-life cluster data, kindly donated by our partners at Nokia and Ringer Axel Springer Poland. It contains a production data from a real-life cluster and not a synthetic load. The data was gathered from over 2 years and contains data from about 1,500 machines. It contains the aforementioned low and high-level metrics, such as CPU, memory usage, and also some additional ones, like requests per minute and errors count, and currently reserved amount of pods by the active autoscaler, which allows easy benchmarking since it is possible to compare its reservation behavior based on the system's parameter with proposed solution. The experimental solution has been implemented in Python language with TensorFlow backend for neural networks. The goal of the experiments was to confirm the improvement of including selection function. Therefore, various predictions models were trained and benchmarked alone, and then they were added to the ensemble without any change to their configuration to see how the ensemble would perform. The theory is that the ensemble should have a score at least on par with its best component, since then it would only be using the best component all the time, or should be better than it when multiple components could improve the score at different times. The metrics used were accuracy, which means how close the actual values were to the predictions, measured in mean squared error, averaged over the whole batch. The following figures present the experimental results of the accuracy of pod assignment comparison. Two slices of dataset were used for evaluation, stable and chaotic. The stable dataset contained regular daily cycles of higher load with more pods needed during the day and less during the night, since the users were more active during the day. The chaotic dataset contains data from service which interacted both with users and automatic API tools, which meant that its load was varying over the course of experiment to simulate drifts and shifts in behavior, because the API tools were simulating random load. In the stable case, which could be an easy, although perhaps common one, the best prediction model is a long short-term neural network, which was expected, as recurrent neural networks of this type are known for their high accuracy in time series prediction. In the chaotic case, the ensemble model performed best, outperforming all other models, its components, as we assumed in the hypothesis. The proposed solution may not be best suited for stable cases. However, in less predictable ones, it could prove quite viable. Even though the performance improvement achieved by it in this example is not extreme, it is still noticeable even for such roughly calibrated models that we were using. This confirms that there is need for further research of this method. We have also analyzed the performance over a longer period of time, of up to a month, to see how the model behaves. The results are presented in this figure, in which it is possible to see the model's predictions compared to the actual values. While these predictions are not exact, they follow the trends well. The presented solution can work in cloud environments in which prediction is possible, as mentioned in the beginning, and can reduce the safety buffer and the costs. Additionally, the cluster's responsiveness to peaks can be increased, which is important in services experiencing dynamic changes, such as news websites. The future directions include fine-tuning the existing algorithms and evaluating new ones, adding an anomaly detection module, benchmarking the solution in different scenarios, both in terms of load and service types, including lifelong learning techniques, and finally detecting problems in the cluster, which could perhaps be also done when using the system together with anomaly detection module. Thank you for your attention. Are there any questions?